In this video, I'm going to get into understanding how these Jablonski diagrams we've been learning about translate into practical UV-Vis spectra that we would actually take in an analytical lab. And it's extremely important that you understand this, so make sure you go through this video as slowly as you need to make sure that you're getting it. So our example molecule is going to be triazine, dissolved in a hexane solvent, a nonpolar solvent. We will then contrast this data here with what happens if we put it in a polar solvent. But let's keep things simple for now. Let's understand what we're seeing. So first of all, we should be familiar with spectra by now. It's been a little while since we've seen one, but we're just plotting light absorbance on the y-axis versus longer and longer wavelengths on the x-axis. But we have to remember that wavelength and energy are inversely related, so as wavelength increases, the energy is actually decreasing. But it's actually more useful for this example to think of it the other way, that as we go from right to left, our energy is increasing as wavelength goes down. And so all the way on the right side of the spectrum, at the longest wavelength, lowest energy, we see this little bump here indicating that this particular wavelength and energy of light must be equal to some delta E within the molecule in order to allow for that absorption to occur. Well, since this is the lowest energy light absorption that we see here, then that must correspond to the lowest energy change, which in this case is just the energy needed to excite an electron. In other words, the energy needed to take the molecule from the ground electronic state to the first electronic excited state, but no additional vibrational excitation on top of that. And so whatever this energy gap is here, that's the energy of light that is absorbed. That energy can be translated into a wavelength, and that is the wavelength of light that we are observing being absorbed in this spectrum here. Now, if we look a little to our left, we see that this shorter wavelength, higher energy photon is also being absorbed by the molecule. Well, that must correspond to the next lowest energy transition possible, higher in energy than this one, but lower than the other possibilities. That would be a vibronic transition, where not only are we exciting the electron, but we've also caused the lowest energy excitation in the vibration as well, as described in the prior video. Looking back at the spectrum, we see that an even shorter, higher energy wavelength over here is absorbed, which corresponds to this vibronic excitation here. So when this wavelength of light hits the sample, this is what's actually happening in the sample. This excitation is occurring. And then we can keep on going through this pattern. We see that this even shorter wavelength is also absorbed. That wavelength and energy of light must correspond to this delta E right here. One more time, what this means is that when the instrument shines in this particular wavelength of light, that particular energy of light, it is absorbed and it causes this vibronic transition in the molecule. Not just an electronic excitation, but a third level vibrational excitation. And so on. This wavelength gets absorbed, this wavelength gets absorbed, but we'll notice that as we're getting higher in energy, shorter in wavelength, the peak size is going down. We also notice that earlier, the peak size is getting up as we went shorter. So it goes up and then down. The height of the peak, in other words, the amount of light that is actually absorbed at those particular wavelengths, is related to the likelihood of these transitions happening. So let me make one thing clear. Just because light has the proper wavelength and energy to be absorbed by a molecule doesn't mean that it will be. It might still pass through. It just means that it can be absorbed if the energy matches the delta E in the molecules. But it turns out that if we were to shine equal amounts of photons of these two wavelengths at the sample, so we just shine in this particular wavelength and this one, the sample will absorb photons of this wavelength far more often than it absorbs photons of this wavelength. The reason why one transition might occur way more often than another one is due to a principle called the Frank-Condon principle, which is way beyond the scope of this class. That's another PChem 2 topic. For now, we just accept that some transitions are more likely than others, and there's just no obvious way to predict it without getting into quantum mechanics. And no molecule works the same way. So in this particular molecule, we see that it's actually the second wavelength this transition here that is most likely to occur. This is the largest peak. It's slightly taller than its neighbors. And then as our wavelengths become shorter and our energies become higher, the likelihood of these transitions and absorptions becomes lower and lower, until even though in principle there are even higher vibrational energies that can be accessed, it's so unlikely that we don't really see any absorbance of those higher energy lights. Again, it is very important that you understand how this translates to the practical spectrum. So feel free to rewind this video if you didn't take it all in on the first shot. That's perfectly normal and understandable. One of the most common misinterpretations that students make is they interpret the y-axis here as being identical to the y-axis here. So they think that this particular wavelength, because it's the highest in energy, should also translate to the largest peak in the spectrum. But that's not how it works. Again, why some peaks are higher than others is outside of the scope of this class. In reality, the vertical axis of the Jablonski diagram syncs up to the horizontal axis of the spectrum, like so. Okay, that's really how those two diagrams line up. And by all means, pause the video at this point and make sure that you're seeing how this all connects. Okay, now let's quickly discuss what happens in a polar solvent, like water. Well, what's going to happen is that dipole interactions with the polar solvent molecules will actually affect these energy levels in the triazine solutes, so that these clear and distinct energy gaps are no longer observed. It's kind of like these levels start to wiggle around in energy like so. And so when the energies aren't static and rigid like in the previous picture, the gaps in energies between all these states is also changing, which means we're not going to observe these extremely discrete, specific wavelengths being absorbed while others are not. And the result is our spectrum looks more like this. Everything just kind of merges and spreads out into this broadened hump, as opposed to these discrete finger-like peaks where obviously each of these wavelengths translates to a different clear-cut transition in the molecule. Nope, instead we just get everything merging together, but notice this still traces the general pattern of that spectrum above. The highest wavelength to be absorbed is still at the same spot as before. And so most of the spectra that we'll see in this class from here on out are going to look more like this, because typically we use aqueous solutions in our examples. So let's make some quick notes on this and call it a video. I'll put this in the bottom left corner. In nonpolar solvents, each vibronic transition is observed. Each vibronic transition observed. But in polar solvents, it's usually a broadened hump. In polar solvents, usually a broadened hump. But the highest point should still match the strongest vibronic transition. We'll put that in parentheses. Highest point still matches strongest vibronic transition. So hopefully that all makes sense. Again, feel free to watch this multiple times because it is very important that you understand how everything syncs up. This was one of the major reasons why we covered all that theory in the previous few videos.